Welcome to Study Loop.
Hi, in the given problem, here this is z-axis, this is y-axis, and coming out of the plane of paper perpendicularly, we can consider this is x-axis. And the coil, a rectangular coil, has been given as having a length parallel to y-axis and width parallel to z-axis, like this. So if this is z, then y, and then x-axis. Area of this coil has been given as 600 centimeter square, or we can say this is 600 into 10 raised to the power minus 4 meter square. Its angular speed of rotation is given as 35.0 radian per second, and the magnetic field, which is along x-axis, has been given as 0.450 Tesla. Now, in the first part of the problem, the coil is rotated about y-axis, means like this. In that case, the maximum EMF induced in this coil will be given as the product of number of turns with the angular velocity, with the area, and with the magnetic field. So when we multiply these values, the number of turn is just 1. For angular velocity, this is 35 radian per second. For area, this is 600 multiplied by 10 raised to the power minus 4. And for magnetic field, this is 0.45 Tesla. All these values comes out to be 0.945 volt. This is the maximum EMF induced in the coil when it is being rotated about the y-axis. Now, in the second part of the problem, the coil is being rotated about x-axis, means like this. So when the coil will be rotated about x-axis, no change of flux will take place. So the EMF induced will be 0. No EMF will be induced across the coil. Finally, in part C, the coil is rotated about an edge parallel to z-axis. This is the z-axis. So if we assume the coil to be rotated about this arm like this, so the same flux will be changing through the coil as it was changing in the first part of the problem. So the maximum EMF induced will remain same, which will be given by the same expression. So we'll be having the same magnitude, 0.945 volt. Thank you.